Well, hello everyone, I'm Jason. As Ellen briefly said at the beginning, I'm a general surgery resident at Georgetown in Washington, D.C. I'm in my final year of residency, and I'm doing minimally invasive surgery fellowship next year, which focuses mainly on robotic surgery. And I know Ellen through the Master's in Biomedical Informatics that we did together from 2020 to 2022. I was not, just as like a caveat, I was not a clinical informatics fellow, but at the same time as the Master's, I was sort of working on, working in a lab at BID on surgical informatics, sort of deploying clinical decision aids, building, deploying, and evaluating clinical decision aids for surgical scenarios like management of surgical conditions and when to take patients to the operating room. So thank you guys for having me, and also I just want to very quickly also say thanks to Ellen for proposing that I come chat with you guys about some of the work that I started when I was when I was a master's student, and I've kind of continued because I'm very excited to hear you guys' thoughts, and I'm very grateful to Ellen for the opportunity to talk about this stuff, and so thank you. Two other really quick caveats. One is that I was told in an email when she first told me about this that this is a didactic lecture series. I just want to be very clear that it's not meant to be like a didactic in the formal sense. This is just me sort of sharing a topic that I'm very interested about, and again, curious to hear you guys' thoughts. That's one. And then the other is a little bit of context again about what I did research on while I was here. So as I said, I worked in a lab at VI Deaconess that was run by a trauma surgeon, and we mainly focused on, again, building and deploying and evaluating clinical decision aids for surgical conditions. And one of the things that I noticed when I was doing a lot of this research is that one of the assumptions we often made is that a successful sort of endpoint for a lot of our projects was when the algorithm that we were training and deploying had successfully been deployed and was delivering a prediction to the surgeon. But I think that was almost a sort of false endpoint in the sense that I realized that after deployment, there's actually so much more complexity and unpredictability and heterogeneity in what happens between prediction delivery and the ultimate human decision that is made. And that kind of interaction is sort of overlooked, and so that's what I kind of became interested in researching. I think you might want to. Oh, is it not full screen?
I think you're on the Teams. I think you're like
sharing. Oh, I'm on the wrong one. Sorry, you're in. There we go. Thank you. Perfect. Thanks. All right. So I think a good place to start talking about this topic is actually with chess. So in 1997, Garry Kasparov, chess grandmaster at the time, he lost a match to IBM's Deep Blue, and he actually became fascinated after he lost that match. He became became very introspective about how he played versus how the computer played, and became fascinated with the idea of how humans think versus how computers think, specifically as it relates to playing chess. And so he started teaching chess with the help of computers in new ways. He started a website, and he taught large numbers of people chess with the aid of computer algorithms. And he actually noticed something very peculiar in his studies and his teachings, and that was that he started noticing that some weaker players were regularly beating stronger players, and specifically he found that less skilled human chess players that were collaborating with the computer algorithm tended to win games. So some of them tended to win games against highly skilled chess players that were collaborating with the same computer algorithm. And with a little bit more study, what he noticed is that the difference between these two groups, the weaker players with the algorithm and the stronger players with the same algorithm, is that the difference he noticed is that the weaker players had well-defined processes for how to interact with the computer's recommendations, and the more skilled players that lost generally did not have any sort of protocol for interacting with the computer. And so as he actually describes in one of his talks, he noticed that there was considerable friction sort of between the intuition, the strong sense of intuition that the more skilled players had about what the best next step should be versus the computer's recommendations, and that friction between the two sort of altered their gameplay in unpredictable ways and often sometimes harmful ways, which is often what caused them to lose matches. And so that sort of gave rise to what is now known as Kasparov's law, which is that a weaker human plus a computer plus a strong interaction process tends to be superior to a stronger human with the same computer but no interaction process, no interaction protocol. And that, of course, so that principle is very, very relevant to medical decision making and clinical decision aids. For obvious reasons, we sort of assume, as I was alluding to at the beginning, that delivering the best possible recommendation to a physician will result in them making the best possible decision, but that's of course not always true because humans respond to algorithmic recommendations in very heterogeneous and unpredictable ways. And ultimately, for a tool that you build to have clinical impact, a physician first has to decide how to incorporate its outputs into their decision making. And so before I actually delve too deep into that topic, I first want to kind of take a step back and kind of lay to rest an assumption that's being made throughout this presentation, which is that there's really no controversy that medical decision making stands to benefit tremendously from clinical decision aids. We've known in the literature since the 1950s, at the very early, 1959, but there are certainly papers that precede this also that show that even the simplest statistical tools tend to outperform physician diagnostic capabilities, very, very consistently. And so, in this paper by Ledley and Weston, they showed that simple statistical tools tended to vastly outperform physician diagnostic capabilities when the computer and the human were both given New England Journal of Medicine Clinical Pathology Conference cases. And many studies since then have shown the exact same thing in different scenarios. So that is an assumption that I kind of wanted to first clarify. So there's clearly an impetus for physicians and algorithms to collaborate effectively, but what does collaboration sort of look like right now between algorithms and humans? And before we even talk about how physicians collaborate with algorithms right now, we first need to understand how physicians grapple with probabilities, and the short answer is that they do so very, very poorly. That sort of intuition of chess grandmasters colliding and exhibiting friction with statistical machine recommendations, and that sort of friction clouding their ability to update their reasoning appropriately is actually not a unique phenomenon just to chess players. Physicians are famously bad at simple probability estimations and assessing pretest probability and updating their thinking based on certain test results. And many studies have shown this, in recent years in literature. But here's an example of one. where physicians were given two pieces of information, both with different probabilities, and were asked to estimate the likelihood of a medical outcome based on those two pieces of information. And I picked this paper in particular because the conclusion highlights that the vast majority of physicians responded with a probability that was mathematically incoherent or illogical, which I think highlights the problem very well, because I think what it highlights is that fundamentally humans, physicians, of course, being among them, are not good Bayesian thinkers, are not good probabilistic thinkers. And that really is the bare minimum skill set you need to have to work alongside algorithms. And that sort of inability to do so prepares us very poorly for incorporating new information from algorithms to update our thinking. So, that sort of randomness and unpredictability is certainly one way to describe how physicians tend to interact with algorithmic recommendations. But there certainly are some common patterns in cognitive biases that tend to arise when you examine studies that study this interaction. And I think this is a nice paper that hints at one of them. So in this study, this research group used an algorithm called My Surgery Risk, which is a nationally very well validated clinical algorithm that uses preoperative variables to predict the likelihood of post-surgical outcomes for patients undergoing surgery. And so these authors used clinical data plus the My Surgery Risk algorithm to predict patients' post-surgical outcomes, and then also asked the surgeons who were taking care of these patients to do the exact same right before surgery. And what you'll find, first of all, this might come as not much of a surprise, but when you have physicians predict various post-surgical outcomes, and you have the algorithm, which uses clinical data, do the same, the algorithm pretty consistently outperforms the human. But that's we sort of kind of have already covered that ground. The more interesting part here is that then, when you tell these physicians, hey, we have a algorithm that outperforms your predictive ability, here's its recommendation as to, or its prediction as to what ultimately will happen to your patients. You show that to these surgeons who have already issued their prediction, and ask them to reassess what will ultimately happen to the patients after seeing the algorithm's recommendations. Almost uniformly, none of their predictive abilities change. And I think apart from this phenomenon that I'd already talked about, which is this idea that physicians don't have a good understanding of how to update their thinking based on new information. It also highlights, I think, somewhat of a paradox, which is, we'll call it predictive dissonance. I think it has other names in the literature, but it's this paradox in which the greatest value of these tools is realized when they change the physician's mind. But in order to change one's mind, they have to deliver information that contradicts your initial intuition. And of course, as it turns out, humans are most resistant to advice that is discordant with their own. And so, in this study in particular, every opportunity for the surgeon to listen to the algorithm's recommendation was an opportunity to improve. And yet, in most cases, that actually didn't happen. Yeah.
In the study, were they given just like a risk number percent? Did it say why?
No, there was.
Based on this.
There was this. This study did not include any explainability metrics. I'll touch on explainability in a little bit. But that's a really good question. So, some have proposed that explainability is a way to help educate physicians using the algorithm on how to best incorporate its prediction into their decision making, but that idea is kind of controversial, and there's evidence on both sides of that argument. So yeah, so this idea of predictive dissonance, I think, is one interesting phenomenon that seems to arise, so this pattern that seems to arise at this interface between physicians and algorithms interacting. A more commonly described phenomenon, which you actually may have heard of already, is called automation bias. And so automation bias, I think, is very nicely highlighted in this study, which was done by Dr. Ghasemi, who's a famous AI researcher at MIT. And she and her colleagues gave radiologists the task of interpreting chest X-rays, but she wanted them to do so alongside a AI assistant. And the AI assistant actually just ended up in this, for the purposes of the study, just being smoke and mirrors. It was just a human on the other end of the algorithm, the algorithm. But what they did was they gave radiologists an accurate prediction. And you can see in this particular case number 3, like this chest X-ray, when you give the radiologists an accurate prediction, then their accuracy tends to approach 100%. It tends to be excellent. But for that exact same scenario, when you give the radiologist an incorrect prediction, their accuracy plummets by 75%. And so this highlights, again, the phenomenon of automation bias, in which, in some cases, the physician, or the human rather, tends to let the algorithm override their own intuition, and essentially exhibit an over-reliance on what the algorithm is recommending. And this phenomenon has also been described sort of very commonly in some recent large headline-making plane crashes, where pilots tend to let an algorithm override their own intuition, of course, with catastrophic outcomes. And so, automation bias is kind of the other end of the spectrum when it comes to cognitive biases that tend to arise when physicians interact with algorithms. So to summarize, the sort of forces at play when a physician is given an algorithmic prediction, there is one, inexperience with probabilistic reasoning, which was highlighted in that first paper. And then there is, again, this idea of predictive dissonance, where we tend to resist changing our minds in the face of new information, or resist, if inexperience with probabilistic reasoning is manifested as our inability to understand how to incorporate the algorithm's advice into our decision making, then predictive dissonance goes a step further and is manifested by us resisting incorporating that information into our decision making. And then at the opposite end of the spectrum, you have automation bias, where we tend to over rely on algorithmic output. And there are certainly other cognitive biases that kind of arise in this space, but I think these are probably the most common and potentially the most important ones. So this brings us to the next section, which is understanding the strengths, the relative strengths and weaknesses of human intuition as it compares to statistical learning. So why not skip right to talking about how humans and physicians and algorithms can collaborate better? Well, first, before you envision ways to create some amazing decision-making paradigm that uses both of them in harmony, you have to understand the role that each of them play. And that's kind of where I became interested in doing some of my initial work in the lab during my informatics time. So I think a good place to start talking about this is with the NISCA first calculator. Are you guys familiar with the NISCA first calculator? Yeah, so it's a very common I would argue it's probably the most commonly used statistical risk prediction tool for surgical patients that's used in the US. It's been validated since I think 2011, and it's been, or 2007, I guess, and by the American College of Surgeons every year on millions of national surgical patients. And it uses some 20-odd clinical predictors like BMI and CKD and lab values, vitals, those sorts of things, to predict a long host of post-surgical 30-day outcomes. Death, discharge to rehab facility, sepsis, those are some of them, but there are many others that it predicts. And in addition to it being a very commonly, widely used risk calculator that we use to predict, to help us predict what will happen to patients after surgery, it is also a nice example of what it looks like currently, as insofar as how we build intuition into risk scores and how we quantify human adjustment. And I think there are some problems with how it's currently done. So. You can see here, if you plug in all the variables for your patient and it gives you some risk estimate of what will happen to them after surgery, you as a surgeon can kind of assess for yourself, is there some context about this patient that the algorithm is not capturing in its 20 preoperative variables? If you think so, then there's a widget on the calculator where you can adjust, you can influence the algorithm's output. You can say, oh, this patient has XYZ condition that's not captured by the NISCOP risk calculator, and therefore their risk of post-surgical adverse events is actually is either somewhat higher, how you define somewhat, that's another question entirely, but somewhat higher than what NISCOP predicts, or significantly higher than what NISCOP predicts. And if you click one of these, then all of these recalculate. And so one of the questions I started out with, that kind of prompted all this was trying to figure out the math behind what exactly is done under the hood of this intuition adjustment. And it's actually very arbitrary. So, if you look under the hood of how this intuition adjustment is viewed, of how it's designed, is essentially it bumps up your patient's risk to either the first national standard deviation or the second national standard deviation of risk for all patients undergoing that procedure nationally, which is, I think, I would argue that it adversely affects the predictive performance of the NISCOP risk calculator. So, for example, for all patients undergoing, say, an exploratory laparotomy, if you plug in your patient's preoperative variables, they fall right here relative to the mean risk for all patients undergoing XLAP in the United States. If you look at your patient and you think, oh no, their risk is somewhat higher, then it completely erases all preoperative variables about that patient and says your patient's risk is at standard deviation number 1 for all patients undergoing this procedure in the United States. Or if you say, oh, my patient's risk is significantly higher, then it says, oh, okay, you fall at the second standard deviation. And as an interesting, additional point, if your patient doesn't fall here but falls somewhere here, then if you plug in somewhat higher or significantly higher than the NISCOP risk calculator's original estimate, then it does not adjust the patient's risk at all. And this is a tool that surgeons across the country have been using for almost 2 decades now. And so I think the question that was inspired by looking under the hood of this model was, how can we understand and characterize surgeon intuition and its role in predicting patient trajectories a little bit more precisely? And so we designed a study that was inspired by that question. And so what we did was, just take a moment to kind of briefly explain the study. First thing we did was recreate a local version of the NISCOP risk calculator using surgical patients and their clinical data at BID units. So we ultimately had, I think it was somewhere around 1,500 patients in our cohort, all undergoing surgery at the BI, and gathered not only their clinical data the same clinical data that the national NISQUIP model uses, but also surveyed surgeons preoperatively. And by preoperatively, I mean immediately before they scrubbed into the case. So ideally, they have all the same information that the NISQUIP risk calculator has access to. Ask them, what is your intuition around this patient's risk of 30-day morbidity and mortality? So we essentially would briefly survey them on that to gather some sense of their intuition as to how they thought this patient would do, and use that as a data source in varying combinations with NISQUIP clinical data to understand what the predictive role is of intuition in predicting how the patient will ultimately do after surgery. And so let's see here. So thing number one is that, or finding number one rather, is that our local NISQUIP model performed pretty much exactly the same as the national NISQUIP model. That's the same AUC that they report in the American College of Surgeons paper. Not entirely surprising. Interestingly, training a model on preoperative intuition alone, so no clinical data, is an independent predictor of how the patient will ultimately do after surgery, but not as good as the NISQUIP risk calculator. Also not entirely unsurprising given what we've talked about already. The third and slightly more interesting finding here is that when you train a model on intuition data plus clinical data, there's essentially no difference in how well the algorithm predicts what will happen to the patient after surgery compared to clinical data alone. So it does do better than intuition data alone, but it does not do better than clinical data alone. So so that's very interesting. So that's one interesting finding, which I'll kind of talk about a little bit more in a moment. But some other sort of interesting patterns we noticed, which actually in many other papers since ours was published in other fields like radiology, pathology actually in other fields, has actually shown to this sort of same phenomenon bears out as it relates to how humans think about how humans react to algorithms, and that is that as patient complexity increases, so one way to measure patient complexity is how many complications they experience after surgery, but there are many other ways to measure complexity, and no matter which way you measure complexity, as patient complexity or acuity increases, the surgeon increasingly disagrees with the algorithm's prediction and wants to adjust it, even though the model's prediction at all strata of acuity is the same. So as the patient gets more and more complex, the algorithm performs roughly the same on relatively healthy patients versus relatively sicker patients. But for whatever reason, as that uncertainty grows, the slide is that no matter what nationally validated model you use, NISQUIP Potter is another one, when you add that intuition to the clinical data that the algorithm is learning from, it doesn't really change model performance. And then perhaps, what I found to be the most interesting finding from all of this, and I apologize, by the way, this is some of the confidence intervals on this are kind of wonky because this is a table from an early version of the analysis we did where I think this only had somewhere around 200 patients in the cohort, which is why the confidence intervals are sort of kind of strange, but the same sort of pattern bears out in the larger 1,500 patient cohort that we ultimately ended up publishing, which is that, so I'll back up and say first, not only did we survey surgeons on their intuition immediately before they scrubbed in, but we also surveyed them on their intuition about how the patient would do in the 30 days after surgery, immediately after they scrubbed out. So essentially, immediate preoperative intuition versus immediate postoperative intuition, and because we kind of wanted to compare the two and see if anything changes. So clinical data, again, you know, it roughly approximates what the national model. So sorry, this is the NISQIP model essentially alone that is learning from clinical data, preoperative clinical data. Preoperative intuition, as I said before, is a reason. This is an okay independent predictor of how patients will do after surgery. Postoperative intuition does quite well alone. And then in our roughly 200 patients initial cohorts, what we found is that when you use preoperative clinical data to train the model, in addition to postoperative intuition to train the model, well, in this case, it essentially predicted exactly how every patient would do after surgery in that cohort. So that combination was the most powerful in identifying what would ultimately happen to patients.
Question?
Yeah.
Can you go back to it?
Yeah.
So I think this is fascinating, and I have like a million questions, but I'm just going to do this one.
Yeah.
I don't want to mess up your flow.
No,
So does this suggest that, because I'm not as familiar with this risk score, so a question I have when we're presenting is this risk supposed to capture like the risk to the patient that something will happen during surgery that will alter their course, or like their underlying phenotype that will cause them to, assuming all the surgeries are kind of roughly equivalent, have a different outcome after?
That's a good question. So the NISQIP risk calculator does not include or infer anything about what will happen during the surgery. The surgery itself is actually just used as a predictor of what will happen after. Like the CPT code you put in ends up being one of the predictors in the algorithm, and does not pass any judgment as to whether a technical error was made during the case or if something unexpected happens during the case. It treats all exploratory laparotomies as the same. And yeah, and so in some sense you could say that the algorithm is basically what the algorithm is doing is, to your point, just capturing the patient's preoperative physiology and using that, like trying to squeeze as much signal as it can out of preoperative data to understand the patient's preoperative physiology, and then estimating what will happen to them after this intervention, after this black box intervention.
And then, if that's the case, do these data suggest that the patient's postoperative course is a combination of both? How the surgery goes and... Yes,
exactly. Okay. That's exactly correct. So yeah, so I think that's probably the most important lesson to learn that I learned from this analysis, which is that, like I said, the algorithm does a very good job of squeezing almost all of the available signal out of preoperative clinical data, preoperative objective clinical data, to predict a patient's outcome. And the human surgeon isn't using that data, that same data, has access to all that same data, but he isn't using it in any more clever way than the algorithm can, nor is it bringing any additional important, valuable preoperative information or context that the algorithm doesn't already have access to, as it relates to preoperative intuition specifically. But where the value of the human contribution does lie is in understanding what happened during the surgery, which the algorithm not only has no access to as far as data goes, but also doesn't fundamentally understand. And what I mean by understand is like, there are some fundamentally unmeasurable things that presumably go into postoperative intuition and make it so valuable, like what the tissues look like, right? I mean, there are so many times, I can say from personal experience, we go into the operating room being like, oh, the CT scan looked really, really terrible. And then the tissues themselves, the quality of the tissue, the tactile sensation or how it looks, or, this liver actually is rock hard. Maybe that means this patient has underlying cirrhosis and is not actually going to do as well after surgery as I thought. Or these tissues look a lot better perfused than I thought they would based on the preoperative imaging we had, and therefore maybe the patient actually will do better than we thought. Those sorts of immeasurable things are the context that the human can capture that the algorithm, again, doesn't have access to in the form of any intraoperative data. But also, even if I would propose that even if you did give it access to intraoperative data like anesthesia, vital records, and those sorts of things, some of these intangible, fundamentally human things like yeah, again, understanding physiology of a patient just by looking at them, like looking at the calcified arteries or looking at the tissues, is something that is very valuable that a human brings to outcome prediction.
But, sorry, last thing.
Yeah.
Your first segment would suggest that if you could capture those intuitions and train a model, then that model would perform better than a human would. Like, if it could accurately represent the human would have flaws that would make it imperfect. Question mark.
Wait, sorry, could you just explain that one?
Like the human intuition based on what they assess during surgery is based on things that they assess during surgery, right? Like things you could measure, things you could input into a model.
Right.
So if you were able to discern what those things were and then put it into a model and train the model.
Like a preoperative model.
Or like a post-op.
Or any model, yeah.
I think like measuring some of the things that you said are currently immeasurable. So like if there was a video recording and you measure like perfusion
yeah.
and like texture of everything.
Yes, that's okay, so I get it. So in some probably not so hypothetical future, near future, I think computers based on say intraoperative video will be able to understand many of the same things that we think are fundamental. Like the things that I'm describing right now that are fundamentally human, like the tactile sensation or the appearance of tissues and those sorts of things, are things that only we can perceive right now. But presumably, as models get more and more sophisticated and also get access to more and more data, we'll be able to supplant our intuition by inferring what our intuition would have been based on a video of what happened during the surgery.
Or audio recording.
Yeah, exactly. I mean, any data stream that's, any intraoperative data stream probably contains some signal of what the human surgeon is thinking. Yeah. It could be like how much electrocautery was used. Like if you got like a log of how much the electrocautery machine was used, that probably contains some intuition signal in it. But in any case, I mean, I think the broader point is that as the algorithm becomes more complex, as the algorithm gains access to more and more data, more and more multimodal data, I think the role of intuition becomes smaller as well. So final section, which is how do we get humans and algorithms to collaborate better, given what we now know about the value that they bring to the table, which again is essentially that the algorithm makes very efficient use of the data that is given, but has a very, very limited context or very limited worldview. Like the worldview of the NISCOP algorithm is 20 pieces of information. That's it. Whereas humans have effectively unlimited worldview. We gather infinite number of variables, some measurable, some immeasurable. But of course, our drawback is that quite simply we're not good at math. We're not good at getting the most signal out of that data that we collect. So if those are the relative strengths and weaknesses, how can we get humans and algorithms to collaborate better? One easy answer is to fall back on the initial point I made about Kasparov's law and have essentially rigid interaction protocols whenever physicians interact with algorithms. And it actually does work. This law that I'm describing is not only something that this chess player observed empirically, but or anecdotally, I should say, but actually bears out in data. So as a brief example, if you give weak radiologists and strong radiologists access to the same AI chest X-ray interpretation aid, and you expose them to a series of different interaction protocols, which if we had more time, I could go into exactly what they are. But in some cases, the weak radiologist plus the AI tool with a good interaction protocol will outperform the better radiologist with the same tool, but a supposedly inferior method of interacting with the algorithm. And so actually, just for a brief bit of context, some of the some of the protocols were, so for example, one of these protocols was a protocol where the algorithm's prediction was weighted by the algorithm's self-reported confidence, as well as the algorithm's historical accuracy. And then the human radiologist also reported the confidence and had a track record of accuracy that weighted their prediction as well, and then you combine the two. And that ended up being a very effective collaboration method for this prediction task. While that is a very effective collaboration method, imagine how cumbersome that would be if every time you had to consult an algorithm, you had to step through all these additional confidence reporting steps and all these other sort of things. And what's I think important to keep in mind here is that accuracy is not the only metric we need to be optimizing for, or at least considering, but also cost and time as well. The best X-ray reports that reports, say, a pneumothorax is not very helpful if it's delivered hours and hours after. Something should have been done about it. So if you have to consider cost and time as variables as well in how humans and algorithms collaborate, then I would propose a alternative collaboration strategy, which is, in some cases, no collaboration at all. And so it turns out that having humans and AI read every chest X-ray together not only does not improve their accuracy, as we've already established, but takes significantly longer than if either one were to do them alone. And so when you balance accuracy with time of reads, and also, as these authors did, with societal costs of an incorrect read, then in many cases it makes sense to delegate most cases to just independent AI reads, in a small fraction of cases where the AI is not confident, to human reads alone. And an even smaller fraction of cases where, in this case, where the societal cost of an incorrect read is extremely high, then there are some edge cases where sometimes it's better for the human and the AI to take a really long time to read the thing, but to do it together. And so I think that I really like this blurb that I pulled out from this paper, which is, we already have established from our research, and also these guys kind of found the same thing, which is that deploying AI assistance has potential benefits, but the biases in humans' use of AI kind of negates these potential benefits, and that when you have humans and AI kind of perform the same task together, it unfortunately just doesn't really improve performance, but it takes much longer than what either would do alone.
I'm so sorry.
No, you're good.
Does that study, I saw like a blurb or something where Trump was in favor of what was the strike, like the dock workers strike a couple months ago, where they were trying to prevent automation from taking their jobs.
Yes.
And Trump was like the whatever like monetary gains might come from automation are much smaller than like the human cost of everyone losing their jobs. So is that factored into like the social cost if you on the previous slide, like if you delegate all of that work to AI, does that cost jobs, or does it make everyone's life easier so then it's like better? Was that part of the study? So
you actually bring up two really good points. The easier one to address, I think, is actually what I really like about this paper is that the authors, they're actually from DBMI, like right across the street. But what they did that I really appreciate is they made no assumption about what the societal cost is of having AI replace positions, or the societal cost of getting a chest X-ray read incorrect. So essentially what you have here is for every possible, so basically the x-axis is just like saying, we don't know what the societal cost is, but for every given societal cost, we can estimate the optimal distribution of AI prediction versus human prediction or combination prediction. That's one. And then the other is, yes, I absolutely agree with your point that there are, ostensibly having AI read, perform a fundamentally a task that traditionally belongs to just radiologists does have a upfront cost as it relates to like lost jobs or wages or views or what have you. But there are downstream additional costs in both directions as it relates to what happens, how you calculate that cost. It's not just the upfront cost of the lost job. There are wages gained as it relates to people being upskilled, entirely new jobs that are created that didn't exist before, and those sorts of things. So so to answer your question, I think calculating the societal costs of algorithmic delegation versus human delegation is very complicated and not just a function of like the lost human productivity. But I don't propose to have an explanation for how to calculate it, and neither do the authors.
What? You don't?
Unfortunately, I don't. So a couple of last really quick points that I do really want to make are so in cases where I think I've established multiple times that in cases where the human brings no additional immeasurable context to the prediction task, their intuition does not add any value to an algorithmic's predictability. That's been established. But how do we figure out what cases are valuable to have human involvement in? Like this little sliver right here, where you want humans and AI to collaborate. How do you figure out what cases those are? Prospective, like before, not retrospectively, where you combine intuition and clinical data and you find out, oh, actually the human did add some value. But before that even happens, how do you figure out what those cases are, and include that in your interaction protocol, where you sort of decide, oh, I can tell you already that this is a case where the physician is going to add some valuable context, and therefore we should have the human and the AI collaborate together. And the way that we're working in our lab on doing that right now is by studying what we're calling this idea of algorithmic equivalency. And first, I should mention, by the way, that the concept for this study that we're kind of doing right now, the credit for it entirely goes to Rohan Allur, who's like a postdoc at MIT, who this is sort of his idea, sort of his brainchild. So I'll make sure to give him credit for it. But so how do we prospectively identify cases where the human brings valuable context that the AI doesn't already capture? This idea of algorithmic equivalency, which is this phenomenon where patients often look identical to an algorithm, but they have very different outcomes. And so, as an example, like how many times have you seen like patients have the same exact, say, like CHA2DS2-VASc score, or like 10 patients have the same CHA2DS2-VASc score, they score the same points on the CHA2DS2-VASc score nomogram, but their outcomes end up being vastly different. The algorithm would have you believe that every patient who has those identical 7 or 9 variables. I don't calculate the CHA2DS2-VASc score often on my own. I kind of leave that to you guys too. But in the finite feature space of that algorithm, every patient who has the same score for the same reasons, the algorithm would have you believe is going to ultimately do exactly the same. When in fact that's not true, right? Obviously, the patients do vastly different, even if the algorithm thinks that they are going to do exactly the same. And so, how do you stratify patients who look the same in a finite algorithmic feature space into multiple different outcomes? And the answer is human input. So if a physician can weigh in on these 10 patients who look exactly the same and stratify them into separate outcomes, in a manner that is better than random, then they must be productively incorporating information that is not encoded in this finite feature space, which is the definition of the valuable context that we've been talking about. And so then the idea would be that, you know, if you are able to accomplish this analysis, then any patient that falls into this group would benefit from human physician input to figure out what outcome they'll ultimately end up in. And then the last point I wanted to talk about, just because you know, Ellen mentioned this at the beginning, is this idea of explainability as a way to facilitate collaboration between humans and AI, or humans and algorithms, I should say. You know, I think explainability has been sort of touted in some papers, at least, as a sort of panacea for helping physicians figure out how to productively incorporate algorithmic output into their decision making. And an example of explainability, like in this case, might be a heat map on a chest X-ray, where the algorithm highlights the most important parts of the X-ray to help the physician figure out how it came up with that prediction. It intuitively makes sense that that would be very helpful. But there is mounting evidence, I think, now on both sides. Some papers that say that it does help, and some papers that say that it doesn't. And this one paper in particular has a very nice study design whereby they deliver accurate predictions to radiologists also reading chest X-rays, and find that the AI plus the human, as we already know, the AI doesn't do a tremendously good job at improving their performance. And when you add explainability metrics to the algorithm, then it similarly doesn't significantly improve their predicted performance. However, when you deliver an incorrect prediction to the algorithm, to the human, their predicted performance plummets, again, as we know. But when you add model explanations to that incorrect prediction, it still does not mitigate the negative effects on human performance. And so I think that the takeaway from this is that, you know, in some sense, clinicians aren't trained to understand or interpret many efforts at explainability. Like some of the more complex models that people are using now, like neural networks that use explainability techniques like shaft values, if you've heard of those before, still require like a PhD in data science in order to understand. So that's one. So I think what follows from that is that there needs to be some additional progress in the science of explainability efforts to make them more effective at helping us collaborate. And then, sorry, last point I'll make with the last minute that I have is one last final important necessary but insufficient measure that I think needs to be taken to aid in human AI collaboration is teaching algorithmic medicine starting in medical school. So Adam Rodman, who's a hospitalist at the VI Deaconess, argued last year, which I think is it's a very important argument, that we need to shift in medical school this idea of pure pathophysiologic reasoning to include probabilistic and Bayesian reasoning as well, and that ultimately would that would solve the problem that physicians encounter in that very first paper I talked about, where that highlights their weakness in probabilistic reasoning. And so again, I think that's a sort of measure that absolutely needs to be taken, but many other collaborative strategies will need to be built on top of that in order for us to make the best possible use of algorithms.
Can I ask a question?
Yes.
Jason, this was great. I think this was very important topic, increasingly important, especially with clinical decision support